Our second numerical method is called Newton's method. So Newton's method is a means to solve equations, and it is related to linearization, but it's got a little bit more steps to it and can create much higher degrees of accuracy. So let's start by looking at equations that you would have difficulty solving. For example, x equals cosine x. All right, how would you solve that? Answer, analytically, you cannot solve that. There's no analytical means to solve that. You've spent your mathematical career so far learning how to solve every kind of equation there is. So you learn to solve first linear equations, and then systems of linear equations, and quadratic equations, and polynomial equations, rational equations, radical equations. You learn to solve trigonometric equations and exponential equations. So your whole career so far has been learning to solve different kinds of equations. So you might be disappointed to know that most equations cannot be solved by any of those means. Here's a simple example. We could have, in fact, any polynomial equal to any trigonometric expression. You cannot solve that analytically except in certain very rare cases. So that's why these numerical methods are so important. So of course, if I encountered an equation like that I knew I couldn't solve, I would just graph it on my graphing calculator, and we have some understanding of how the graphing calculator does this. It just goes, divides the x axis into very small intervals and then calculates the f of x for each point and puts a pixel there. All right, but then your calculator can also do this. We can solve it, as you know. We can just go second calc, and let's calc the intersection, right? And so it asks, is that your first curve that you want to use? Yeah. Is this your second curve? Yeah. Then it asks you to guess. What value you're going to use. And we're about to find out why we do that. So I want to be somewhat near the intersection where I think the intersection is. And then see, here's what we really are going to be studying. I press the enter key. The calculator hesitates for a second, and then it says the intersection point is 0.73908513. Right? How did it do that? That's the question that we're about to look at. Newton's method is one of the main ways to look at an equation like this and solve it through a numerical computational process that not only leads to the result, but in many cases can lead to the result to any desired degree of accuracy, as long as you're willing to put in the number of floating point operations that are necessary to do it. All right, so we're not going to start with this one as our example. What we're going to start with is this one. We're going to estimate the solution. So these are estimating techniques, but remember, all decimals are estimates of irrational numbers. The solution to this we can certainly guess is irrational. So anything we write down as a solution is an estimate. The only question is, how accurate is that estimate? Anything we write down as a decimal anyway. All right, so we're going to estimate the solution to x cubed minus 2 equals 0. All right, so a couple of words about the problem. So first of all, this is an equation. So this method, Newton's method, is used to solve equations. Now, of course, you could rewrite that equation and realize that all you're really doing is, we know x is going to be the cube root of 2. So what you're really doing is estimating what the cube root of 2 is, and you could do that with linearization. So we're going to see that Newton's method will allow us to estimate this solution, which happens to be the cube root of 2, to a greater degree of accuracy than linearization does, but takes an investment of work. So the other thing is, in Newton's method, we're always looking at an equation equal to 0. So if we wanted to solve this equation, by the way, we would rewrite it as x minus cosine x equals 0. So we're always solving an equation equal to 0, and so we're essentially always looking for the x-intercepts of equations. But any equation, regardless of what it is, you can rewrite the equation in such a way that that's what you're doing. So you just find a function that you can set equal to 0, and Newton's method finds x-intercepts of functions and therefore solves equations. All right, so looking at this equation, So what does it look like? What does our graph of f of x look like? So we can draw that. Be really aware of your parent functions and transformations. This is x cubed, so we know that looks like the classic cubic, and it's shifted down by 2. So it has we now know a horizontal tangent here at 0, 2. And so it goes like that, and it goes like this, a little bit like that, a little bit like this. And here's the magic point that we're looking for. All right. I'm going to show you what this method revolves around. The method revolves around a starting point. So you pick any starting point. So you look at this equation and say, what would be a place to start? I know that 2 cubed is 8, so maybe we'll start with that. I happen to have started this with x equals 3. Just, was pick a number. X equals 3. Probably not the best number really in this case, but that's what I did, so we're stuck with it. All right, so here's what it revolves around. You have a point up here, which is 327. What we're really looking for is this point down here. So what we're going to do is follow the tangent line back to the x-axis and find this point. All right, so if we go up to the graph and follow the tangent line down, we're going to be closer to the x-intercept than we were in a graph like this. And so as you going through, be aware of how the shape of the graph is going to influence how quickly we obtain a solution. So we're going to call this point that we started with, we're going to call it x1. So we could also call this point x1, f of x1. And what we're going to do is we're getting this second point here, which is x2. And in fact, that's the point x2, 0. So basically saying we're going to start at a certain point, that's our first x, and we're going to get a second x from that. Now, the reason that Newton's method can achieve high degrees of accuracy is because it doesn't just stop there. It is an iterative method. So that means that what we're going to do then is once we get the second point, we're going to do it again. Go up to the graph and follow the tangent line down. And you can see how my x3 is going to be really close to that x-intercept. So if we exaggerate the graph, we'll see how it might take several steps to really get to the x-intercept. But that is the process, okay? So we're going to look at how these 2 points can combine with the derivative, in the slope of the tangent, and we can, knowing x1 because we picked it, how do we calculate x2? So that's what we're going to look at next.